Bismillahirrahmanirrahim. Wassalatu wassalamu ala rasulillah. So today we will solve recitation problem for chapter 12. As I already said, I solved already 7 or 8 problems that are already posted on Blackboard. So now here I will solve some problems that I did not solve on Blackboard. So go on Blackboard, okay? And you will take advantage of what is posted there. I put the recordings, but also I put the slides. The slides have the solutions. So enjoy and make good use of this material. Okay, now, first problem I want to solve is this problem here. So what do we have? We have a solid copper sphere. It's a uniform sphere, and I give you the radius. The radius of this solid sphere made of copper. This is our initial, okay? 85.5 centimeters. The question is, how much stress should be applied to this sphere to reduce its radius to 85 centimeters? This is our final, okay? So here I have a uniform compression. Uniform compression, I apply uniformly a stress around my sphere, and the sphere shrinks from 85 centimeters of radius to from 85.5 centimeters to 85 centimeters. So the question is, how much stress should I apply to get this reduction? Of course, here I give you the bulk modulus of copper, 1.4 10 to the power 11. So you know that in a uniform compression, okay, the stress F divided by A is proportional to the strain. And the coefficient of proportionality is a bulk modulus. B multiplied by strain in a uniform compression will be delta V divided by V. Okay. Good. So here I gave you B, 1.4 10 to the power 11 Newton meter square. Now I have to multiply by delta V divided by V. Of course, as I told you, this delta V, I mean absolute value. Because when I have uniform compression, the final volume is smaller than the initial volume. So here I mean absolute value. So what is the change in volume? The change in volume will be the final volume minus the initial volume. But if I take the absolute value, it will be the initial volume, 4 pi divided by 3, initial radius cube, minus 4 pi divided by 3, final radius cube, divided by the volume. By the volume, I mean the initial volume, of course. So 4 pi divided by 3, initial radius multiplied by. Okay. Of course, I will simplify by 4 pi, and I will get this. Okay. So I will just have what I have, 1.4 Newton, 10 to the power 11, sorry, Newton meter square multiplied by 85.5 cubed minus 85 cubed divided by 85.5 cubed. Okay. I did not replace it. I did not put it in meters because I know that it's a ratio, so it will cancel. It will, simplify. But I can put it in SI units. Anyway, my final answer will be in Newton meter square. So here, in any units I put them, same units, of course, they will cancel out. So you use your calculator, and of course, you will get this 2.4 10 to the power 9. Okay. And this is equal to F divided by A, and this is a stress that I need. Now, if I want it to be a little bit more picky, I will ask you, what is a force? What is a uniform force? The magnitude of the uniform force. So you just need to multiply by the area. By area, I mean the area of the sphere. It will be 4 pi r square. Okay. So you just take this number, you multiply by the area, and you get the force, the magnitude of the uniform force around my sphere. Okay, this is pretty straightforward. Let me go to the second problem here. So in this second problem, what do I have? So I have a horizontal aluminum rod, and I give you the diameter of the rod. The diameter is 4.8, so that means the radius is 2.4 centimeters. So it projects 5.3 centimeters from the wall. So this is my wall. Let me just, okay. So I have a rod which is horizontal. It's made of aluminum. And the length of this rod is what? L, 5.3 centimeters. You don't need to draw, but we are in physics. I prefer drawing. And this diameter is 4.8 centimeters, meaning the radius is 2.4 centimeters. Now, I take a 1,200 kilogram object, let's say a car, which is suspended at the one end of the rod. So I suspend it here. Let's say I suspend here a car, okay, which has a mass the mass is what? 1,200 kilogram. So I give you the shear modulus of aluminum. Shear modulus is for aluminum is 3.0 10 to the power 10 Newton divided by meter square. So I neglect the mass of the rod. Now the question is find the shear stress on the rod. And then the second question is find the vertical deflection at the end of the rod. Okay. So you see this rod here. Though it has a negligible mass, it's able to support a car. Okay. This is some nice engineering going on here. Okay. A small rod made of aluminum can, do this. Anyway, how practical is that? I don't know. I did not do the experiment, but this is something to think about. Okay, now here, of course, the force that I'm applying here, F in magnitude is just mg, because basically I have a static equilibrium. And this force here is a shearing force. The stress is a shearing stress. Why? Because the force is perpendicular to the cross-sectional area here. Okay? Sorry, not perpendicular, parallel. Okay. So this force is parallel to this cross-sectional area, so it's a shearing force. Now, here I am asking about the shear stress. Of course, shear stress is F divided by A. And again, F is like this, okay? So I want to calculate F divided by A. So how should I get it? Of course, I know the magnitude of F. What is the magnitude of F? Is the magnitude of mg. I know also the cross-sectional area is pi r square. So I will have 1,200 multiplied by 9.8 divided by pi r square. Of course, I have to put r in meters, 0.02, of course, 24 square. Okay, so this is my shear stress. If you do it, I believe you will get 6.5. How much do you get? 10 to the power 6 Newton meter square. Now this shear stress will do what? It will deflect, of course, my rod slightly in the vertical direction. So the question is, what is this deflection delta x? Assuming that I am still in the elastic regime, I know that shear stress F divided by A, which is the number that I found here, is equal to shear modulus G multiplied by delta X divided by L. So I know the shear stress, I know the shear modulus, I know the initial length of my rod, I know what is delta X. And you will find that delta X is 1.5 10 to the power minus 5 meters. Okay, it's very, very small, of course. You cannot see the deflection, the vertical deflection, but it's here because of the shearing force. Okay, so this is straightforward. Any question? If you have a question, don't hesitate. Okay.
It's straightforward.
Very straightforward. Okay, good. Now, let's look at this problem here, which is down. So here I have water, which is freezing. And if it's not straightforward, don't be shy to ask a question. When water is freezing, it expands by around, let's say, 9%. Now, the question is, what should be the pressure increase inside the radiator of your car if the water is frozen there? Okay. When you put the water was, let's say, liquid. You live in Canada, Ontario, it's very cold, the water freezes. And of course, the freezing water will expand its volume, okay, by 9%. So what should be now the pressure increase inside your radiator? So first, you should exploit this data. 9%, which is 0.09, of course, is just the change in volume divided by the initial volume. Delta V divided by V. Okay, it's a ratio between the change in volume, but here I have what? I don't have a uniform compression, I have a uniform expansion. Okay, so my object is, let's say, expanding. If I have uniform compression, of course, my object is shrinking uniformly, but here my object is expanding uniformly. So delta V is positive here. I don't need to take the absolute value. So this is 0.09. And you know that the stress, uniform stress in a uniform expansion or compression is F divided by A, is bulk modulus multiplied by delta V divided by V. So this stress is also a change in pressure, okay, because I have what? I have a liquid involved. Okay, so delta P, which is the stress, actually I'm just asking you what is the extra stress due to the expansion of my liquid of water. Okay. So I know the bulk modulus, 2 10 to the power 9. I know delta V divided by V, which is 0.09. I just calculate and I will get 1.8 10 to the power 8 Newton meter square. But remember, Newton meter square, when I have, of course, a liquid, this is just Pascal. Okay, and this is the answer. Okay. Good. Now, let me go to the next problem here. And both of them, I gave you the solution already. Okay, I will skip this, very interesting, but from what I see, it's straightforward for you. Solve this problem 28 and this problem also, the solution I given here. Okay, now let me go to something more interesting. Static equilibrium. Okay. The part about elasticity, you can solve it. Now let me go to static equilibrium. When I have static equilibrium, well, what you need to remember is two things. Net torque around any point is 0 because I have static equilibrium, but balance of forces along X and Y is 0. Now here, let's see what we have. So we have a force here, F of magnitude 15 Newton, shown in the figure. So this force F keeps the hanging mass, the hanging block of mass M, and the massless pulleys in equilibrium. So this gentleman here, this block here is in static equilibrium. This pulley 1 is in static equilibrium, but also this pulley 2 is in static equilibrium. But here I made sure that these pulleys are massless, okay? Okay. And they are not rotating. They don't have a moment of inertia, okay? Massless. Of course, they have a radius, but they are massless. Because their mass is negligible compared to the mass of the block. So now the question is, what is the mass of the block? So first, I have static equilibrium. So I have balance of forces, balance of torques. Now let's use it in a proper way. Here, I will look at the block first, and then I will look at pulley number 1 and pulley number 2. Block 1, of course, you have the weight downward, mg downward. And then here I will have a tension 1. Let me call this one tension 1. And here I will have a tension 2. Okay. So if I use balance of, basically it's a static equilibrium. If I use balance of forces on the block, I will just have tension 1 plus tension 2 is equal to mg. Okay. The force that is pulling up are equal to the force that are pointing downward. Okay. Just on my block. This is for the block. Now, let's look at the pulley number 1. So for the pulley number 1, I will first apply the balance of torques. I'll say net torque around the center of mass of the pulley, which is here, is just equal to 0. Okay. So of course the radius here is the same. So this is telling me that basically, okay, you will have minus FR plus T1R is equal to 0. So R goes away. So I'm telling you that basically T1 is equal to F, which is equal to 15. So of course, this tension 1 here is equal to 15. Because in order for it to remain in equilibrium, I have F, which is pulling in the negative direction, but I have also T1 here in the perspective of the pulley is, rotating in the opposite direction, in the positive direction. In magnitude, they should be the same because the momentum is the same. So I come back to my equation here. This will just give me 15 plus T2 is equal to mg. Now I just need to get T2. Okay. How do I get T2? I have applied balance of forces on pulley 1. Now let me apply a balance of torques on pulley 1. Let me apply now balance of forces. Net force on pulley 1 along the y direction is equal to 0. So on pulley 1 here, I have, of course, 15 Newton downward, but here I have T1. T1 is also 15 Newton, but I have something pulling upward here. Okay. This is basically, let me call it T3, if you want, or let me call it F3. Okay. So net force along Y for pulley 1 will give me basically F3 is equal to 15 plus 15, which is 30 Newton. So basically this force here is equal to 30 Newton, just by balance of forces, okay, along the Y direction. Now, the same thing, now, that means now if I look at pulley 2, I will have 30 degree downward, but here also I will have 30 Newton, okay? Because I need this pulley 2 to be at equilibrium. So if I look at pulley 2 and I say net torque around the center of mass is 0, this is just telling me F3, which is 30 degree, is equal to T2. Okay, 30 Newton. Why I'm saying degrees, I don't know. 30 Newton. Okay. So T2 is 30 Newton. I will come back here and I'll plug it here. So I will have mg is equal to 15 plus 30 Newton. So basically I have m is just 45 Newton divided by 9.8, which will give me 4.6 kilograms. Okay. And the answer is here. Okay. So you just need to you can solve it quickly if you want. Okay. I just took my time to show you the different steps. Okay. Any questions about this? No. Okay. Straightforward. Let's go to the next problem. And this problem, I gave it as a quiz last year. Not last year, in term 182. Okay. 181, 182. Excellent student, by the way. Okay, so what do we have here? And you can see the solution in my website. I will show you. So I have a uniform beam, and I give you the weight of the uniform beam, 150 Newton. So basically, if the mass of the beam is small m, mg is 150 Newton. It's uniform, so that means the weight is applied right in the middle of the beam. So right here. So I have mg is 150 Newton. So this uniform beam is hinged to a wall, supported by a fin cable. So it's hinged here, okay? And then I have a fin cable which is attached also to the wall, as shown in the figure below. Okay. First question, draw a free body diagram showing the force acting on the beam. So the beam is my system. I look at all the external forces that act on the beam. Of course, I have 150 Newton here. due to the weight of the beam, which is applied right in the middle of the beam because it's uniform. Here, at this end, I have 300 Newton. Why? Because, well, I have this massive object which has a weight of 300 Newton applied here, and it's vertically downward. Here, of course, I will have tension of the cable, TC. Now, here, of course, I will have the force on the beam from the hinge. I will decompose it into two. The first one will be F horizontal. Actually, this is a normal force. It's normal to the, wall. But also I will have an F vertical upward. Okay. Because the beam will have a tendency to slide down, of course, but the hinge has to keep it static. So you have an F vertical. Okay. If it was not hinged here, this F vertical, if in order for my beam to be at static equilibrium, this F vertical should be what? A static friction. Okay. If I did not hinge it, I did not, let's say, fix it, I still will have friction between the beam and the wall. And what will play the role of F vertical is a static friction, because my beam should be static. And you know that static friction is equal to mu S Fn. But here Fn is equal to Fh. It will be mu S Fh. Okay. Okay. But here I did not leave it like this. I did not leave the friction do the work. I hinge it. So I don't need the static friction. It's already hinged. So first question, this is my free body diagram. You do this, you get how many points? 3.5 points. This is Sadaka, actually. Okay. You should, you all know how to do a free body diagram. So you will not have 0, I hope. Okay. So you will have at least 3.5. But that's not enough. Now the second question is, what is the magnitude of the tension of the cable? So where should I put my axis such that in one equation, in one shot, I will get the tension of the cable? Hello.
Along with the 300 Newton.
So you want to put it here, the axis of rotation. If I put it here, the torque of TC will be 0. So I cannot get TC because the torque of TC will be 0. And if I put my axis of rotation, my pivot point at the hinge, I will say that this is the X direction and this is a Y direction. And I will say that my beam is at static equilibrium. Net torque around O is 0. So in one shot, I will get rid of FH and FV because net torque will be what? It will be torque of FH plus torque of FV plus torque of, let's say, mg being 150, plus torque of 300 Newton, basically capital Mg, if I could this call capital Mg, okay, plus torque of Tc, this should be 0. This should be 0 anyway. If I choose my axis here, axis of rotation here, pointing towards U, or here, anyway. But if I want to get Tc directly, I better put my axis of rotation here at the hinge, such that the torque of FH is 0, because now FH is passing through the pivot point, and FV also have 0 torque. In one shot, I get rid of 2 unknowns. And here, my only unknown will be Tc. Now, what is the torque of mg? 150. So you know that torque, I have 3 formulas. Torque is equal to Rf, torque of force F, Rf sine phi. Or it will be R perpendicular F, moment R multiplied by F. Or it will be R multiplied by tangential force, F perpendicular. So here I will be using these two. Okay. For mg, the best thing is to use R perpendicular F. Why? So X, my axis of rotation is here. I just need to draw the line of action for the weight of the beam. Okay, this is a line of action, and I look at the perpendicular distance. the perpendicular distance will be L divided by 2. Okay. So the torque of mg is negative because it will make it rotate clockwise. So minus L divided by 2, basically 4 divided by 2, which is 2, multiplied by F, which is 150. And what is the torque of the 300 Newton? I draw the line of action of this force, and I look at the perpendicular distance. I'm using this formula here, R perpendicular F. Okay. So what will be the moment arm? It will be L, basically 4 meters. Okay. I gave you 4 meters multiplied by mg, which is 300 Newton. Now, what is the torque for TC? The torque of TC, I have to use this formula here. Okay. So first, TC will have a positive torque, so it will be plus. R, what is R? R is this. So R is equal to L. Multiply by TC, multiply by the sine of the angle between R and L. Basically the sine of this angle that I call phi here. Okay, because R is in the positive X direction and TC is like this, so the sine of the angle is this. But sine phi is just equal to sine theta, because these two angles are supplementary. Okay, if you add them, I get 180 degree. So they have the same sign. Let me say it again. Sine phi is equal to sine theta. And now what is sine theta? In the problem, I gave you the length. Okay, this is a triangle which is rectangle. 4, 4, 3, and 5. So sine theta will be equal to what? Opposite side divided by hypotenuse. 3 meters divided by 5 meters. Okay? And this should be equal to 0. So I know everything. Well, this is my equation. The only unknown is TC. Okay? I'll have minus 2 multiplied by 150 minus 4 multiplied by 300 plus 4 multiplied by the unknown TC multiplied by sine theta, which is 3 divided by 5, and this is equal to 0, and I get TC. So if you do it, you get TC is equal to 625 Newton. Okay.
Teacher?
Yes.
If I choose theta between 5 meter and 4, it will be correct or not?
So if you want to choose what?
Theta, not phi.
Not this theta, but I call it theta already here.
Yes.
Okay, so it's already called theta. But of course, if you want to use this one, you know, the triangle is a rectangle, right? The angle will be the sine of the other angle. Okay, so, but if I call it theta, I want you to call this theta. If you want to use another angle, you call it something else. Okay, so you do this, you get 3.5 points. Okay, so that's already 7 points out of 10. Now the last question is, find the magnitude of the horizontal component of the force on the beam from the hinge. Basically, find FH. How can I do to find FH? Of course, I will use balance of forces. Net force along X is 0. So along X here, I will have plus FH. It's positive along X. But which other force has a component along X?
TC.
TC. But now, which component of TC? It will be a cosine or a sine? Theta. Let's say theta. Okay. Now, look, this is what I want here. I want this component here of TC. Okay. So it will be minus TC cosine. Okay. If this is theta, I have a cosine theta. And this should be equal to 0. So FH is just TC, and I know TC 625 Newton multiplied by cosine theta. Now you have to say me, what is cosine theta? Of course, it will be adjacent side 4 divided by hypotenuse, which is 5. So 4 divided by 5, you do it, and it will give you 500 Newton. This is F horizontal. Okay. Now, bonus point. Nice gentlemen, we are in Ramadan. If I am to give you this quiz, I will give you a bonus point, of course. MashaAllah. So now find F vertical. Okay. So if I want to find F vertical, let me just share it here. Okay. So this is it. Okay. If I want F vertical, you can find this in my website. Okay. I will apply net force along y is equal to 0. Along y, I have only 2 forces, of course, or 3 forces. I have F vertical, but also I have the sum of the 2 weights. Okay. But don't forget also, I have also the y component of TC. Okay. So let me admit this student. So I'll have F vertical is the sum of the 2 weights, okay, 150 and 300. But now I have to deduct the y component of TC, which is T sine theta. And I will get 75 Newton. Okay. Now, let's go to the second problem, which I gave my students as well. So this is it. Okay. Let me go maybe quickly here. Okay, let me stop sharing and come back here. Oops. Okay. Let me go back here. Okay. Yes, Hussam, go ahead.
For the previous question, can we use balance of torques and place it like in the middle or on the right, because we have the other forces to get the horizontal component?
Yes, you can do it. You can use balance of torques around any point. So here's a smart move was to use balance of torques around O to get TC. Now, once I get TC, instead of using balance of forces, you can use again balance of torques. Okay. Anyway, you have 3 unknowns and you need 3 equations. These 3 equations will be 1 balance of torques and 2 balance of forces along X and along Y, or you can use 3 balance of torques around 3 different points. Okay. Yes. Okay.
Yes, got it.
But the thing is, you do what is suitable for you and you get me the right answer and don't make a mistake. That's all what I, want you to realize. Okay. Now let's look at this problem here. I have a uniform beam as well, weight 60 Newton. Okay. So 60 Newton will be right in the middle here. And it's going down here. Okay. So the beam has a length of 3.2 meters and it hinges here at this lower part, this lower end. And at the top end, I apply a horizontal force F of magnitude 50 Newton. Okay. Draw a free body diagram of all the external forces acting on this beam. So of course I will have this F, 50 Newton. I have the weight, 60 Newton downward. I have also here the tension of the cable, TC. And here I will have what?
F vertical. Oh, it's
And F vertical. Okay. By the way, this F horizontal, I really don't know which direction it will go. It will be in the positive X or in the negative X. Okay. But let's see, copy it in the positive X. If I solve it, I will find that it's positive, that's true. If I find it's negative, that means it's going in because it depends on the, these 2 gentlemen, TC and F. Which
won't it be like the Fs? It will be negative because the force is to the right.
No, it's positive here, actually, because the force is to the right, but you have the tension pulling back. So now it will be a balance there. You get my point? Which
Yes.
is balancing? Which one is bigger? And these are reaction forces. They adapt to the situation, actually. Okay? FH and FV adapt to the situation depending on, what's the magnitude of F and what's the magnitude of TC. And they will adapt to keep my object in static equilibrium. Okay, so here it will be positive, but it's not obvious. I can say negative as well. If I say negative, at the end, I'll find that it's positive, okay? Because for this set of parameters. Okay, now let's solve. So the free body diagram was the first thing. So I have, of course, the weight downward. I have F horizontal and F vertical. I have this F. I have 3 points. Okay. Now, the second question, what is the magnitude of the tension in the cable? Where should I apply the balance of torques to get the tension right away? Net torque around O is 0. Where should I put O? I should put it at the hinge, of course. And this is x-axis, and this will be my y-axis. Okay. So I will have, of course, net torque will be here, only the torque of F plus the torque of TC. All the rest will have 0 torque. The weight now is a radial force, is passing through O. So he will not rotate whatsoever. Okay, so the torque of the weight is 0. The torque of FH is 0. The torque of FV is 0. Okay. So now what is the torque of F? Torque is RF sine phi or R perpendicular F. I will use R perpendicular F for this one. I will draw the line of action for the force. And I will look at the perpendicular distance between O and the line of action. So the torque of force will be negative, because it will make my object rotate in the negative direction. So I'll have minus R perpendicular is 3.2 multiplied by F is 50 Newton. Now TC, on the other hand, will have a positive torque with respect to O. So it will be plus, but TC, I will not use R perpendicular F. It's not smart. What is smart here is to use as angle sine phi, because here I give you the angle 25. That means this angle is 65. Okay. So what is the moment? What is the R? R is this distance here. So it will be 2 meters. Multiplied by F. So here is TC. Multiplied by sine phi. What is phi? Phi is the angle between R. This is R and this is TC. So I want this angle here. This is the angle what I call phi. So angle phi, sine of angle phi is just sine of 65. Because phi and 65 are, you know, the sum gives you 180. And this should be equal to 0. So I know what is TC. Okay, I know everything here. TC is the only unknown, and you use that to get TC. How much did you get? For those who did it, 88.3 Newton. Okay. Now, once I get TC, the second question is, what is the magnitude of the horizontal component of the force on the beam from the hinge? What is FV? So I can do what Hussam suggested, or I can do something else. Okay. So here I will use net force along X is 0. Okay. What are the forces along X? Along X, I have FH plus FH. It's purely along X. But also I have this F50. It's purely along X. Which other force do I have along X? TC. But which component of TC? This component of TC. Okay. And to get that component, it will be plus TC sine 65 degree, which is equal to 0. Because this is 65, and this is the opposite side, so it's sine. If I took 25, so this is 25. This is 25 here, this angle. So it will be cosine 25, of course, because sine 55 is cosine 25. Complementary angles. So I find FH will be just what? Of course, here it's a minus, don't forget, because it's, you know, it's in the minus direction. FH is in the positive direction, F is in the positive direction, TC is in the negative direction. So here it's a minus. So I will have plus TC 80.3 multiplied by sine 65 minus 50. And this I do it and I'll find 30 Newtons. So FH is equal to 30 Newton. So what I guessed was right. For this set of parameters, FH is in the positive X direction. Okay. but some make.
Because tension is higher than the force, bigger than the force.
Because basically, it's not only that. It's bigger, but basically, you know, it's not because tension is bigger than the force, but what is important here is tension sine the angle. Okay? The tension can be bigger than the force, but the tension sine the angle can be smaller than the force. So just be careful with that, okay? Good.
Okay.
And here, if I put my force, of course, I will put it, let's say 80, you know, the situation will be different, for instance. Okay, so I will stop here. You can solve this problem as well. Very good problem. Don't use balance of torques here. Use balance of forces. Because I gave you this angle here is 30 degrees. I gave you this angle here is 70 degrees. I gave you T1 and T2. Everything is in static equilibrium. So I'll choose this as my origin, this as my positive x-axis, this as my positive y-axis. Okay? And I will say that the balance of forces is equal to 0 because this point is at equilibrium. Okay? But here I will have this tension 3. But tension 3 in magnitude is equal to just to the mass of this object, mg. Okay? So if I do the balance of forces, actually I will have here an equilibrium problem. I will have T1 plus T2 in vectors plus basically mg is equal to 0. If I project along x, balance of forces along x, basically net force along x is 0. Okay? So that means T1x, I can get T1x. T1x will be minus T1 cosine theta 1 because I need this. It's minus because it's here. Of course, this is here. So it's minus T1 cosine theta 1. Okay? T2x is plus T2 cosine theta 2. And mg does not have a 0. So this is T2x. Okay? So I have my first equation, two unknowns, T1 and T2. Now along y, I have net force along y is 0. That means along y, I will have T1y, and T1y will be what? Plus T1 sine theta 1. Okay, what is T2y? It's negative, minus T2 sine theta 2. Of course, these theta are absolute value, okay? I take them positive, and the minus, I put it here. And then I will have minus mg, because mg is downward here, basically T3 is 0. And I have my second equation, two unknowns. I shuffle them and I combine them and I get T1 is 66 and T2 is 26. Okay. So that's it for this part. Now, the rest, I have solved this problem in the recitation, in the recordings that I posted on Blackboard. Have a look at it. It's an excellent problem, an A+ problem. I did not solve it using center of mass. I solved it using net torque is equal to 0. So I choose, this is x-axis, this is y-axis, and this is my O, and I said that net torque is equal to 0. Of course, I have to calculate the torque of this side, the torque of this side, and the torque of this side. Moment arm. Have a look at it. It's in the recordings on Blackboard, chapter 12. I have solved this problem as well. Here's a hinge. It's not hinge. The friction is playing the role of the vertical force. Have a look at it. It's an excellent problem. I have solved this problem as well. Excellent problem. This problem, here, excellent problem on Blackboard. Okay. In the Blackboard, there is a typo, and I put it on note so you can see where is a typo and you correct it. This problem, okay. I have solved also this problem on Blackboard. Also this problem on Blackboard. Okay. So now the ball is in your hand. Okay. So please make a good use of it. And that's it for this chapter. Assalamu alaikum. Bismillah wa salatu wa salam ala rasulillah. So we already solved 4 problems from chapter 12. So I will proceed in solving other 4 or 5 problems, inshallah. So we already solved this problem in class. Okay, this one as well. this one as well. We solved it in class, and I gave the solution. You can find in my website. This was also a quiz I gave a couple of years ago. You can find the solution in my website, and we solved it already in class. So today I will solve this problem here. Okay. So here I have a uniform rod. So the rod is uniform and has a mass of 10 kilogram. I'll call it capital M, and a length of 4 meters here. Okay, so this I call it capital L. So it's a uniform rod. The weight is applied in the middle of the rod, and this has a magnitude mg. Okay. Now what happened is I attach here a block of mass small m. So I have here another weight, the weight of the block, which should be small mg. Okay. So as you see, this end of the rod is attached to a rope, and the rope is attached to the wall. So obviously here I will have tension TC of the cable, and the other end of the rod is in contact with a rough surface. Okay, so just by the fact it's in contact, here I will have a normal force that I will call F horizontal, but also I will have a vertical force here that I will call F vertical. Okay, F vertical, and of course this F vertical here is a frictional force. Okay, in other problem it's a hinged vertical component of the hinge, but here it's played by the frictional force. You have friction between the rod and the surface, and because the surface is rough, so the coefficient of static friction is given, mu s is given, okay, between the rod and the wall. Now the question is, what is the minimum distance x from point A at which this additional mass of 5 kilogram will induce a sliding? Okay. Okay. Basically, you can look at it as a minimum distance or maximum distance. Okay. So beyond this distance x from A, well, here it's a minimum distance because it's a minimum distance from here, but maximum distance from here. Okay. Minimum distance from A, beyond, well, this will just slide down. Okay. The frictional force will not be enough to keep my rod in equilibrium. So here I already did the free body diagram on my rod because my system is a rod. So now I have the tension of the cable, and I have the weight of the rod, I have the weight of this small mass, and I have the horizontal force, and then I have the frictional force, which is a vertical force from the wall. So let me apply the balance of torques. My rod is at equilibrium. The balance of torques at point A is equal to 0. So why I choose point A? Because the torque of these two guys will be 0. Okay. Around A, the torque of FV equal the torque of FH is 0. I'm talking around A, of course. Okay, because these two forces are applied at A. So my balance of torques is equal to 0. So I will have 0 for these two torques. Now, what is the torque of this mg? Okay, the small mass, of course, it's negative. So it will be mg multiplied by moment arm. What is the moment arm here? Of course, it's x. Okay. So here I just use the fact that this is my line of action, of course, and the moment arm is this distance, and it's x. Now, what is the torque of the weight of the rod? It will be negative as well. So here I will use also, it will be magnitude mg multiplied by the moment arm, and the moment arm is what? L over 2, right? Good. Now, finally, what is the torque of TC? So the torque of TC, of course, will be positive. It will be TC multiplied by Well, here I will not use the moment arm. I will use torque is equal to RF sine phi, phi being the angle between R and F. So I will have R here is equal to L, which is the length of my rod, TC multiplied by sine between R and TC. So the sine of the angle is this angle here. Okay, I want the sine of this angle. But the sine of this angle is 180 minus theta. So the sine of this angle will be sine theta. So it will be L TC sine theta, and this is equal to 0. So I have my first equation. Okay. So first equation, how many unknowns? 2 unknowns. I don't know TC, but also I don't know X. Now let's get TC. How can we get TC? Let me apply balance of forces. Net force along X should be equal to 0. Okay, so what is the net force along X? Of course, I will have F horizontal plus F horizontal minus TC, but here I need this component here, so it's a cosine theta minus TC cosine theta, and this is equal to 0. So that means F horizontal is TC cosine theta. And again, I told you that this F horizontal is equal to F normal, okay? Because F horizontal is equal to F normal. It's the normal force, okay? Normal to the surface of the wall. So here you have 90 degrees, of course. Now let me apply net force along Y is equal to 0. So along Y, you will have what? So of course I will have the F vertical, okay? Plus TC sine theta. I want this component of TC. And this should be equal to the sum of the weights. So what is the sum of the weights? Of course, I will have M plus M G. Okay. So these forces pointing downward are equal to the forces pointing upward. Okay, so you remember that FV, as we said, is a frictional force. And the frictional force is mu S Fn. But what is Fn? Fn is TC cosine theta. Okay. So I will replace FV by mu S Fn. Now what is Fn? Fn is TC cosine theta plus TC sine theta is equal to total mass G. Okay. Okay. So now here I can get TC. What is TC? Of course, TC is equal to total mass G divided by mu S cosine theta plus sine theta. You take your calculator, you calculate. I believe you will get something like 146.8 Newton. Okay. Just use your calculator. You know everything here. You know MES, you know theta, you know M, 2M. So this is your TC. Now, once you get TC, well, you plug it here in the net torque. Okay. Net torque is equal to 0, balance of torques. So basically this will give you X is equal to what? Of course, TCL sine theta divided by mg minus ml divided by m2m basically. Okay. Okay. So that means the critical X, which is a minimal distance, you just replace everything, you get 3.21 meters. Okay. So this is what we did, and you see that it's 3.21 meters. Okay, that's the minimal distance. So I gave you the solution, and of course I gave you the solution before, but I just redid it. Okay, so if I wanted to ask this problem in another quiz, I will hide this mu s here. Okay? And I will give you the distance. Okay? And I will ask you what should be the minimal static frictional force to have a static equilibrium. Okay. Now let's go to this problem here. So I have in this figure a uniform beam of weight 222 Newton. It hinged to this wall here, as you can see, and the other hand is supported by a wire. And I give you the angle is equal to 30 degrees, theta is equal to 30 degrees, with both wall and beam. Basically, this is 30 degrees, this is 30 degrees. So here you have an isosceles triangle. Okay. So first question, find the tension in the wire. Second question, find the magnitude and direction of the force on the hinge of the hinge on the beam. So let's do a free body diagram. So let's say that my beam has a length L. Okay, I'll call it L. Okay, the beam has a length L. And L is not given, but anyway, we don't need it. So here, the weight of the beam will be applied right in the middle, half L here. You will have 222 Newton. Okay, so I'm doing a free body diagram on the beam. So you have the weight of the beam, you will have the tension of this wire. Let me call it TC, tension of the cable. Here at the hinge, of course, you will have the normal force, and that normal force, I will call it F horizontal, but also I will have the vertical force, okay? F vertical. And of course, here, it's not played by a frictional force, right? Because I hinge it here, so it's static. So I have static equilibrium. This is my free body diagram on my beam. So now I want the tension. Of course, if I want the tension, better for me to choose my axis of rotation O here at the hinge. Okay, so this is my x-axis here, and this is my y-axis. So let me apply balance of torques around O. Net torque around O is equal to 0. My beam is in static equilibrium. So let's calculate the torque. Of course, as you know, the torque of this F vertical and F horizontal is 0 because they are passing through the axis of rotation. So what is left is the torque of the weight. It's negative, it's minus. So let me call this number 22.2. Let me call it mg. Okay, so it will be minus mg. This is the magnitude of the torque minus clockwise mg. Now what is, so I will use this formula, okay, Rf sine phi, okay. So F is mg, okay, R is L over 2, is this distance from the axis to the point of application of my force. Now what is sine phi? Of course, phi is the angle between R, which is here, and the force. So phi is this angle. So I want to find this angle. This angle is the same angle as here. Okay. So how to get it? Well, I know here I have 30 degrees here. I have 30 degrees here. So this angle here is 180 minus 30 minus 30. So basically 120. So that means that this phi is equal to 60 degrees. So this phi is equal to 60 degrees. So here I will have sine 60 degrees. Okay. By the way, you remember that sine 60 degrees is equal to cosine 30 degrees, right? So if I use, instead of this formula Rf sine phi, I use torque is equal to moment arm F. Well, you have to plot the moment arm. So the moment arm, I have to first draw the line of action of the force. So the moment arm will be the distance between O and that line of action. So if this is 60 degrees, this will be 30 degrees. So basically it will be, you know, L over 2 cosine 30 degrees, okay? You do it the way that you want, but get me the right answer because now you are expert in vectors. Good. You either use this formula, or then you can use R F perpendicular if you want, okay? Now this is a torque of the weight. Now what is the torque of TC? Well, I will apply RF sine phi also. So the torque of TC is positive. It will be TC. Now what is R here? Well, R is equal to L. It's the distance between here and here. It's L. Now sine phi, of course, sine phi will be this angle here. This is the angle that I want, okay? But that angle will be just 180 minus theta, okay? So sine phi will be give you sine theta, and theta is 30 degrees, by the way, okay? And this is equal to 0. So you see L simplifies. So I end up with TC is equal to what? Is mg sine 60 degree divided by sine 30 degree, okay? Now, if you put your numbers, you will get, of course, how much? 192 point, let's say 3 Newton. So this is your TC, just by the balance of torques. Now, the second question is, what is the magnitude and direction of the force of the hinge on the beam? So I need to find F horizontal and F vertical. So net force along X is equal to 0. So along X here, well, I have plus FH minus, now I should have the X component of TC, okay? Okay, so how to get the F component of TC? Well, TC is here. So TC is making this vector. So this is TC if I just translate it here. And by the way, this angle here is equal to what? Is equal to what? 60 degree, okay? So this angle is 60 degree here. So if I project, I will have minus TC cosine 60 degree. So I know F vertical, F horizontal is just TC that I found before, cosine 60 degree. You calculate, you get 96 point, let's say 13 Newton roughly, okay? At the end, I will consider the number of significant figures. Now net force, of course, along Y. Now along Y, you will have plus F vertical, of course. You will have what? Minus, of course, mg, but also you will have plus TC sine 60 degree. And this should be equal to 0. Okay, so that means if I change, I just solve for F vertical, I will get what? Basically mg minus TC sine 60 degree, and it will give you 55 point, let's say 6 Newton, okay? Or 55.5 if you want. Okay, now knowing, of course, F horizontal and F vertical, I can get the magnitude of the force on the hinge, of the hinge on the beam. So force of the hinge has two components, of course, so F horizontal square plus F vertical square. Okay, so I can get it. Okay, and I get 11.11 Newton. Now the angle, so the angle is straightforward, right? So you know how to get the angle if I know the component, and inverse of the Y component, which is F vertical, divided by the X component, which is F horizontal, you will get 30 degree. Okay. So this is what I did here, and I already send you this solution. Okay, I solve it, TC, I get 192. Then I solve the rest, I get my answer. Okay. Now let's look at this problem here. So this problem is combining chapter 9 with chapter 12. So I have a mass, basically a hammer. This is small m, and I give you the diameter. So basically I'm giving you the radius. What is the radius of my nail? Okay, you know it. Of course, you have to put it in meters after. Okay, and the hammer strikes on this, let's say, cylindrical nail vertically downward. During the strike, I gave you the duration of collision, and I give you the magnitude of the change in momentum, which is an impulse. So the question is, what is the average strain in the nail during the impact? Okay, so the average strain, you know that stress is F divided by A is equal to Young modulus E multiplied by strain. So the strain here is delta L divided by L. Okay, so this is what I want here. Okay, now let's get the force. Well, we know the Young modulus, we know the cross-sectional area. What is the cross-sectional area? Of course, it's pi r squared. Of course, you know, r is half of the diameter. So the question is, what is the average force? Well, let's get the average force. You know that impulse delta P is m delta V by definition, okay? But it's also equal to integral of F dt, F being the collision force. When the collision force is constant, or I approximate it by an average, I will have F average, of course, multiplied by delta T. So the average force, F average, is equal to change in momentum, which is an impulse here, delta P, divided by the collision duration, okay? So I know everything here, of course. I know this is 900 kilogram meter divided by second. This is 0.11 seconds. So I know the average force. Once I know the average force, I know this A, I know E, I know what is my average strain, and that's it. So this is what I did here, okay? So the average strain is just stress divided by E. Stress is this, and this I know it from here, and you get it, and you know that the average strain is 9.8 10 to the power minus 5. Okay, straightforward and interesting. Now let's look at this problem here. So this problem is very interesting as well. You know, it goes this problem. You see this problem, I made it simple. I gave you this theta is the same as this theta, but I can make it such that this length is different from this length, meaning this theta, this angle here will be different from this angle. Now I will ask you the same problem, but now with different angles. Okay, so you have to find them. So in this problem, I made sure that this angle here, phi, is different from this angle here. Okay, of course, this angle is different. So here, this angle here is 45 degrees, if I'm not mistaken. This angle phi is equal to what? 30 degrees. Okay. Now the question is, what is this angle here? Okay. Well, this is geometry, basically. Okay. So let's find this angle. If you find this angle should give you 15 degrees, actually. Okay. 15, 45 minus 30 degrees. Okay. How do I know? How do I know? Okay. So you know that this is a triangle, of course. Okay. So the sum of the angle is 180 degrees. But also this angle is 180. This angle here is 180 minus 45. So this angle is 15 degrees. Okay. I will come back to this. That's the only difficulty here. Now I have this system. So I have a strut or a beam, which is uniform. Okay. And then I hang this mass here. Okay. So M is equal to, capital M is equal to what? 225 kilogram. Okay. So small m, which is the mass of my beam, is equal to 45. Okay. So I have this cable here, and it's holding the other extremity from my beam, and this extremity is hinged. Okay. So you see the system. Now the question is, what is the tension in the cable? And then what is the horizontal and vertical component of the forces on the strut from the hinge? So here, this is my beam. Let's do a free body diagram on the beam. So of course, I will have the weight of the beam, which is small mg, small m being 45. And then here, of course, I will have the weight of the block. Okay, so capital Mg. Of course, here it's hinged. So that means here I have a horizontal component of my force. And then I have the vertical component here, which is a normal force, by the way. Okay, it's normal to this surface. So I have a vertical force here. And here I will have the tension of the cable. Okay, so this is the first question, to get this tension. And the second question is to find this FH and FV. So this is the free body diagram on my beam. Now, what do we do? Of course, we want TC. I will have to put here my axis of rotation. And this will be, of course, my x-axis. And this will be, of course, my y-axis. So I will apply basically net torque around O is equal to 0. Now let's get the net torque. So of course, the net torque of this FH and FV is equal to 0. So what is the net torque for the weight? Okay, you have two ways or three ways. Either you use torque is RF sine phi, or R perpendicular F, or RF perpendicular, as you wish. Okay, here let me just use RF sine phi. So of course it will be negative, so I will have minus. What is R here? R will be L divided by 2. Again, L is not given. L is the length of my beam. Okay, you will see that it will be a common factor and it will go away, the length of the beam. Okay. Okay. Now, R is L divided by 2. What is the magnitude of the force? The magnitude of the force is mg. Now, what is sine phi? Sine phi. Phi is the angle between R. So this is R. And this is mg. So basically, I want this angle here. Okay. So what is this angle here? Okay. This angle will be 190 minus this angle. And by the way, this angle is what? This angle is 55 because this angle is 45, right? So this angle is 55. Okay, good. So I will have sine 55 degree. And again, sine 55 degree is equal to cosine 45 degree because these angles are complementary. Cosine 45 degree. Okay, good. So if I used this formula, R perpendicular F, the moment arm will be L divided by 2 cosine 45, which is sine 55. Again, you do it the way you want, but get me the right answer, of course. Okay, so here, now this is a torque for the weight of the beam. Now, what is a torque for this weight of the block, or the tension? The tension in this cord here. Remember, the tension in this cord is in equilibrium with the weight of the block. So it's like the weight of the block is applied directly to my beam. So I will have minus. So of course, I will have mg. Now, I will have R sine phi. R is equal to L here. And sine phi, so again, what is sine phi? It will be sine 55. Okay, this is 45, so this is 55. So the angle that I want is 180 minus 55, and you know that sine 180 minus alpha is equal to sine alpha. Okay, good. So finally, I want now the torque of the TC. So torque of TC will be plus TC, of course, multiplied by L, multiplied by sine 15 degree. And this should be equal to 0. So I know everything. My only unknown is TC. So what I did here is this, okay? You see here, I did the same thing basically, but here, of course, this I replace it by sine 55. And here, of course, it's sine 55. Okay, because cosine 45 is sine 55. Okay, the first one I used this one. The cosine, you will get this one. It's the same. Okay? Then this one, of course, we already have it, TCL sine 15 degree. Okay? This angle here is 15 degree. And again, this is a difficult part here to find that the angle is 15 degree. Okay, so if you don't get that point, do it again. Okay, so TC gives you this. Okay, again here, instead of cosine 45, it's the same thing as sine 55 degree. Okay, and you get your TC. Once you get your TC, now you do balance of forces along X direction, and you get FH, the horizontal force, and then you do the balance of forces along the Y direction, and you get FV. Okay, okay, these two forces here. Okay, same as usual. Okay, good. I hope it's clear. If you can solve this, well, you are good for the exam. Now let's look at this problem here. So here, what do we have? We have three situations in which the same horizontal rod is supported by a hinge on a wall at one end and the cord at its other end. Without any written calculation, well, that's, you can do a small calculation, of course. Rank the situation according to the magnitude of A, the force on the rod from the cord. So same, all of them are, uniform rods. Of course, you have the weight, same weight, mg downward, of course, mg downward, the same mg applied at the same point, which is the middle, mg downward. Of course, in each of them, you will have the tension of the cord, and the tension of the cord will be different. So here, I'll call it TC1. Here, I'll call it TC2, and here, I'll call it TC3, okay? And of course, here I'm doing the free body diagram and each of them. So here I will have the horizontal FH1, and here I will have FV1. Here, of course, I will have FH2 and FV2. Here I will have FH3 and FV3, okay? Now the first question is, of course, here I have a static equilibrium problem. So balance of forces and balance of torques. Balance of forces along X and Y, balance of torques around any point, okay? So without any written calculation, rank the situation according to the magnitude of the force on the rod from the cord. So I want this TC, okay? So how will I do? That's my question. So how will I do? Okay. So what I will do here is, as I said, okay, this is not working. So I have to. Okay. So I will have what? Let me start by balance of torques. Okay. Because I know anyway that you should have balance of torques around any point O should be 0. But balance of forces along the X is 0, but net force along Y should be 0. Okay. Okay, I will have to redo this anyway. So this is the weight. This is the weight mg, and it's the same applied at the same point. Okay. So now the question is, I want to rank this tension here. TC1, TC2, and TC3. Okay. I'm doing it very fast, and my handwriting is very bad on the tablet, so bear with me, okay, and redo these problems. So of course, here I will have the horizontal component of the force from the hinge on the beam, and you will have the vertical component. Here, of course, you will have horizontal component, vertical component, horizontal component, and vertical component. Okay, good. So this is my free body diagram on each of these cases. Now, I want this force here, TC, okay? And I want to rank them. Of course, I will choose my axis of rotation here first at the hinge. So if I do my axis of rotation here, well, I get rid of the torque of these two guys, F horizontal, sorry, and F vertical, okay? So I will have to get basically torque of TC plus torque of gravitational force should be equal to 0. So in magnitude, torque of TC in magnitude, okay, is equal to torque of gravitational force in all these three situations in magnitude, opposite in direction, of course, okay? Here I use it around the balance of torques around O. So what is torque of TC? Of course, torque of TC will be equal to what? For the torque, I will use RF sine phi. So the R here, of course, is L, the length of my rod. TC sine phi. Now again, the phi is the angle between R and TC, basically this angle here. Okay, so here I need this angle here, which is 90 degrees. Here I need this angle here, which is 40 degrees. So of course, this should be constant. Now that means if L is constant and L is constant, now the bigger sine will give me a smaller TC for a constant result. So sine, if sine is large, of course, TC is small, okay? So that means, well, sine is largest at 90 degrees, so TC is smaller here, okay? So basically, in terms of magnitude, these two gentlemen will be the same for TC. Why? Because basically here you will have 40 degrees, okay? And here also you have 40 degrees. So for the question number A, what do you have? You have TC in magnitude is the same for 1 and 3, so tie, okay? For 2, it's smaller because you have sine, of course, 90 degrees here. Okay, so for question number A, we have 1 and 3 tie, and then 2 is the last one, okay? Is a smaller TC, okay? Because it has a larger sine phi. Okay, now let's look at question number 2. I want you to redo this, okay? If it's not clear, please redo it. That's why my writing, I want you to redo them and convince yourself, because that's the only way you will learn. Okay, now the second question is, I want to rank the vertical force on the rod from the hinge greatest first. Now, how should I do? You remember in the first question, I put my axis of rotation here. Okay, okay. Let me, this is the weight, this is the weight, this is the weight. This is the TC, this is the TC, this is the TC. And this is the F horizontal, this is the F vertical, of course. This is the F horizontal, this is the F vertical. This is the F horizontal, this is the F vertical. I want you to redo it, okay? Now in the first question, I put my axis of rotation at the hinge. Now let me put the axis of rotation here at the other extremity of my rod. Okay? If I do this, what I am doing, actually, if I use the balance of torques, let me call it point A here, point A here, and point A here, okay? So if I use net torque around A is 0, okay? Why? If I put my axis of rotation here at O, I'm automatically getting rid of the torque of TC around A, which is 0, but also I'm getting rid of the torque of F horizontal around A. okay? Because both the F horizontal and TC are passing through my axis of rotation. So net torque around A is equal to 0 is just telling me that the torque of the weight of the gravitational force in the free situation plus the torque of the vertical force is equal to 0. So the torque of gravitational force is the same for all of them. The torque for vertical force as well is the same for all of them. Okay, so that means for all these free situations, the torque of the vertical force is equal to a constant. And what is the force per vertical force here? It's just R perpendicular F. And you see in all these free situations, the R perpendicular is the same because the R perpendicular is the length of the rod. Okay, FV. Okay, so that means for question number, so for question B, the vertical force have the same magnitude in all the three situations. Okay, let me repeat that. Net torque around this point A will give me 0. That means torque of gravitational force plus torque of vertical force is equal to 0. That means in magnitude, the torque of vertical force is the same for all these three different situations. So now what is the torque for the vertical force, which is a constant, is R perpendicular, F vertical. And R perpendicular here is what? This length, which is a constant. So that means FV is a constant for here, here, here. So for B, you have all tie. Okay. Again, be smart. I use R perpendicular FV, okay, because it's straightforward here. If I used R FV sine phi, okay, well, you will see also that sine phi is equal to 1, okay, because you have 90 degrees between R and FV. Now, the final question is to rank the horizontal force on the rod from the hinge greatest first. So how can I do that? Now, in this question, let me use just the balance of forces. Net force along X, because I want the horizontal force, is equal to 0. So what is the net force along X? Well, you will have, of course, F horizontal, okay, minus TC, okay, cosine an angle, let me call that angle theta, is equal to 0, okay? So what is theta here? Of course, I want the X component. So the theta is here, 40 degrees. So this is the component that I want. Well, here it's 0 because basically theta is 90 degrees and you don't have any force along the X direction. So here I know that FH, sorry, is 0, okay? And you see it because theta is 90 degrees, FH should be 0. And here you will have the same thing. So in magnitude, I'm talking about in magnitude, you have these two tie, the F horizontal here and F horizontal here have the same magnitude, and the F horizontal here is 0. Okay. Okay, good. So of course, in direction, now here, of course, this F horizontal is opposite. Okay, because this T C here is positive, so the F horizontal should be negative here. Okay. On the other hand, this F horizontal, because TC is pointing in the negative X, the F horizontal should point in the positive X. But, you know, the F horizontal for case 3 and case 1 are equal in magnitude, but opposite in direction. So here it's not like this, it's going on the opposite. Okay, so the solution is given. And again, this is a solution. For A, 1 and 3 are tie, and then 2. For B, all of them are tie. This is the vertical force. Okay. And for C, the horizontal force on the rod from the hinge, 1 and 3 are tie in magnitude, of course. One of them is going in the positive X, the other one is going in the negative X. And then, you know, 2, which is 0 here. Okay, a very simple problem, but you need to bring the right argument or the simplest argument to solve it. Okay, I will skip this problem because this problem we solve it in class. Okay. We solve it in class using this rod and adjustable forces. So I have to check balance of forces and balance of torques. Okay. Let me do it here. So obviously this cannot be in equilibrium because balance of forces is not respected. All the forces are pointing in the same direction. Okay. Now let's look at the balance of torques. Well, this one will respect not only balance of force, but also balance of torques. This one, well, no balance of force, no balance of torques. This one, both of them. So this one will be in static equilibrium, in equilibrium. This one, you have balance of forces, but what about balance of torques? Yes, you can check the balance of torque, you will have both of them. So this is in equilibrium as well. This one, you can have balance of forces because you have 2F in the positive X, 2F in the negative X, but balance of torques, no. Why? Let me put my axis of rotation here. It cannot be in equilibrium because it will rotate counterclockwise, okay? So the correct answers are A and C. And we solved this in class already. So that's why I went very fast. Okay, well, here also it's kind of straightforward. We solve it in class, but you have to be rigorous, okay? So this mass here, M1, is equal to 48 kilograms. Now this moment arm is equal to L, and this moment arm here is 3 times L. So if I choose my balance of torques around here, I know that if here I have 48 kilograms, so here I'll have 48 divided by 3. Okay. So what is 48 divided by 3? You will have 16 kilograms here. Okay. But this 16 kilogram will be, you know, you have a balance of forces along the y direction. So you know that this weight, this mass plus this mass should give you 16 kilogram. Okay. Okay. So this one is 3 times less. So basically you will see that this one will be 12 kilogram and this one will be 4 kilogram because of the ratio of the moment arm, of course. Okay. So here if I have L, here I have 3L. So here if I have 12, here I have 12 divided by 3, which is 4. Okay. And of course here, of course, M3 will be 3 kilogram. And here you will have how many? 1 kilogram. Okay. Good. So actually I use balance of forces and balance of torques. Balance of torques, I use them here at this to get rid of, because here you will have this force, okay, to get rid of the torque of this force. And then I find the ratio of these two masses, okay. But I have to say also balance of forces, you have 16 should be counterbalanced by 12 plus 4, which is 16, okay. Okay, I went very fast, but do it properly and get it right, okay. I use balance of forces and balance of torques. So if I use balance of forces, let me just use it here or here. Let me use this here. Balance of forces. Net force along Y is 0. So I will have basically 16 is equal to M2 plus something here, which is 4. But that 4 will be basically, okay, M3 plus M4. Okay, so this is 4. Okay. Okay. Did you get my point? I hope so. Okay. Okay. So 48 here, 16 by balance of torques around here. So I will have, because this guy will be plus, let's say M1 GL should be equal to plus, let's say something here that I call alpha mass G multiplied by 3L. Okay, the G goes away, the L goes away. So I know that alpha should be M1 divided by 3, which is 16. Okay, so have a look at it. Okay, it's nice, it's simple, but don't be confused. So this is a solution, as I said. Of course, you have 48 kilogram here, here you have 12 kilogram, here you have 3 kilogram, here you have 1 kilogram. Okay, good. Okay, we solved this problem in class. I already solved this for section number 4, I believe. One way to solve it is to use the center of mass. But I will give you a better way. A better way is to use net torque around O is equal to 0. So what is my O? This will be my pivot point. I'll choose this to be my x-axis and this to be my y-axis. Okay. Good. So this is x, this is y. Now let's use net torque is equal to 0. So this part, I call it part 1, part 2, and part 3. Part 1 has a length L, part 2 has a length L, part 3 has a length what? X. Good. So now I will find torque of part 1. Let me call it FG1 plus torque of FG2 plus torque of FG3 is equal to 0. So all of them are uniform, of course. So the gravitational force is applied right here in the middle here. Okay, this is FG1. This is FG2. And this will be applied at x over 2. And this is FG3. Okay, good. I'm going very fast. Okay, so torque of FG1. Well, I will use torque is equal to R perpendicular F. So R perpendicular, so this is the moment arm. So R perpendicular is this. So it's L over 2. So with respect to this, it's minus. Okay, so it will be minus L over 2 M1G. Okay. Now, what is the torque of this gentleman? Okay, line of action is here. So it will be minus L. So the moment arm is L. And M2, well, M2 is the same as M1. They have the same mass. Okay, let me put it M1 because they have the same length and it's uniform. Okay, okay, multiplied by G. Okay, now for this, it will be plus. Of course, it will make it rotate positively. So what is the moment arm? This is a moment arm here. Okay, so this is X over 2 and this is L. So the moment arm will be X divided by 2 minus L. Do you agree with me? It's applied here in the middle. So if this is L, so this is X over 2 minus L. Okay, multiplied by M3 G, and this is equal to 0, of course. You see the G simplifies. Okay, now what is M? Well, here, of course, it's a uniform rod. Okay, of course, a rod, by definition, the spatial or the radius is very small compared to the length. So I can introduce my density. So the density, let me call it rho or mu if you want. Okay, but mu is equal to mass, not divided by volume, but divided by length. Okay? So this density here has a unit kilogram per meter because I have a rod. Okay, and by definition, you know, the radius is very small compared to the length. Okay, okay, so this is what we call a linear density or a mass per unit length. It's not a volumic density. Okay, volumic density will be a mass per unit of volume, but a linear density will be a mass per unit length. Okay, so that means M1 will be equal to what? Will be equal to the density, the linear density rho, multiplied by the length. And this is equal to M2 as well, because they have the same length. Whereas M3, well, it's simple. I have the same linear density multiplied by X. So you know that this M here, you will have in all of them rho. Okay, the rho, like the G, will be a common factor. I can simplify with the rho, which is the density. So I will have what? I will have minus L divided by 2. Now M1 is rho L. So I have to multiply by L. Okay. Minus L M1, which is rho L again. So the rho goes away. So I have another L, which is remaining. And here I will have, of course, X divided by 2 minus L multiplied by M3, which is rho X. Rho goes away. So I just have an X here. And then I have, this is equal to 0. So this is the equation that I have to solve. Okay. Good, let's go for it. So here you will have L square divided by 2. Here you will have L square. So here you will have minus 3 divided by 2 L square. And now let me distribute this. So if I distribute, I'll have x squared divided by 2 minus, of course, xl, right? And this is equal to 0. So let me multiply everywhere by 2. And then, so I multiply this by 2. Of course, I will have x squared minus 2xl minus 3l squared is equal to 0. And you see, this is the equation that I have to solve. And this equation is the same as this equation here. And you know how to solve a quadratic equation. Of course, I will have two solutions, either 3l or either minus l. Of course, 3l will be the right one. Okay, so x is equal to 3l. Okay, so this is the one that I want you to use. Network is equal to 0, and you get the different arguments. Again, do it again to convince yourself, watching it. That's why I'm writing very badly. Well, it's not only because of my tablet. Okay, the tablet, of course, I'm not comfortable with it. So, but I want you to redo it by yourself. So all the arguments are here. The ball is in your hand, and inshallah, you know, solve it correctly, and then you'll get the right answer. Okay, for these things, well, they are straightforward. You know, you use the modulus of elasticity. You know, you use this relationship that we used. Basically, stress is equal to modulus of elasticity multiplied by strain. And you do it correctly, and you will get them. There are other problems. I cannot solve them all. So I stop here, inshallah. So please solve them. If you have questions, don't hesitate to ask. Thank you very much. And let me say something before I end. Congratulations, mashallah, you did well in the online assignment. The average is around 7 for all sections. And in our sections, well, the average is around 8, okay? You have one section that has 7.9, 7.8. So basically section 4 and 5, and section 4 and 6, section 5 have an average of 7.3, I believe, okay? So you are above average. So keep the good work, keep the momentum, and work hard, and everything will be all right. Thank you. Assalamu alaikum.